Okay, so I'm going to just rotate that figure which we just saw, since I want the double pendulum to be this way. Okay, and the second link. So let's call this θ1, and θ2 is the angle made by the second link with respect to a frame fixed to the first link. So that's θ2. And then I need to have the center of mass. Let's just put it somewhere right here. And we'll say that the distance is C1. For the first link, it's C2 for the second link, and you'll be able to change that in the code because that will be a free variable. And then let's say that the link lengths are L1, L, let's call them L. Okay, and finally I need to choose the axis. So what we'll do here is we'll fix the fixed frame as x0, y0. The frame one, so based on the correction I just did, the frame one would be right here, y1, x1, and then x2, y2. And let me name the points as P and Q. This is P, this is O. Let's call this point as Q. Okay, zoom it a little bit. Okay, it's a bit of cluttered, but I hope you can see it because of the colors I've used. Okay, so what I'm going to do now is, well, let me, before I just forgot a few variables. Let me define gravity. Let me define this to be mass M2, inertia I2. And then this one is mass M1, inertia I1. And let me put down the, so first what we do is derive equations of motion of the double pendulum. Okay, and so what I'm going to do is essentially follow the recipe I've talked about in the previous class about using Euler Lagrange equation. So the first step is to define the position of the center of mass of each of the links. Okay, that will be, let's call this G1 for the center of the first link, G1, and G2 for the center of mass of the second link. So position of G1 and G2 in frame in the fixed frame or O, x0, y0. Okay, so what we do is we'll use the formula we've written in the past for rotation and translation. Here we want position of G1 in frame 0, and that will be related to the rotation matrix associated with frame 1 with respect to frame 0 times the position of G1 in frame 1. Okay, so let's write that down. The left hand side is simply x G1, y G1 in frame 0. The rotation matrix, okay, now you could be careful. When we define the rotation matrix, we always define the angle theta to be between frame from axis x0 to the link. Okay, so x0 is here and the link is here. So you just can't take a shortcut in saying that this is the angle, because that angle is clockwise and we always define angles counterclockwise direction. So what we need to do here is define the counterclockwise angle from x0 to this link, and that is going to be highlighted, this angle. Right, so you can see that it is it's actually 90 plus 90 plus 90 plus theta 1. So 93 times is going to be 270 plus theta 1. So I'll write it as cosine of 270 plus theta 1 minus sine 270 plus theta 1 sine of 270 plus theta 1 and cosine 270 plus theta 1. Okay, and then I need to find the position of link or of center of mass G1 in frame 1. What's frame 1? Frame 1 is basically this frame. Okay, you can see that this frame is has the origin at O, and so this length along frame 1 or along x1 would mean that the position of G1 along x1 is going to be C1, and distance of G1 along axis y1 is going to be 0. So we have 0. Okay, so simplifying the cosine and sine terms here, we get sine theta 1 cosine theta 1. So sine of 270 plus theta 1, that's basically negative cosine, and that's why we have positive, because the negative signs get cancelled. So then cosine theta 1 and then sine theta 1. Okay, so somebody asked, is the angle 90 twice? No, it's 3 times, because we have 90, 90, 90, and then theta 1. Okay, so it's 270. xg10, yg10. And so I'm going to just simplify this now. If you do the math, it comes out to be c1 sine theta 1 negative c1 cosine theta 1. Okay, somebody asked, could it be written as minus 90 plus theta 1? So this angle, minus 90 plus theta 1. So the thing with going clockwise is that you will have a sign issue. If you don't get the sign right, then a convention is counterclockwise rotations are positive. So you got to be careful. There is a way to do it with counterclockwise over here. And I just want to avoid it, just because I think if I show 2 ways, then people are going to be confused. But there is a way to also look at the angle this way, and also ensuring that the sign is correct. So I would not want you to be confused with this. Always look at angles counterclockwise direction, like with the way I've shown you. Okay, so that's all hard work to get the position of G1. We also need to get the position of G2, because remember, we want to eventually find the velocity of G1 and G2. So let's find position of G2. So G2 in frame 0. Trying to find the position of G2 in frame 0. That will be, first I need to translate the point to point P. So if I know position of P, then I can use P0 plus R1 0 G2 in frame 1. Okay, so this is basically, okay, if you like, maybe aside. So G2 in frame 1 is R21 G22. Okay, this is the formula which basically tells me how I can find position of G2 in frame 1 given the axis P, X2, Y2. Once I do that, then I can find the position in frame. This is basically giving me the position of G2 in okay, never mind. This is just the translation plus rotation formula. Okay, this is basically copied from that lecture. Okay, could you back up? I missed the last line of notes. Okay, here it is. Okay, I'm going to move on. Okay, so G20 equals P0 plus R10 times, subbing this, we have R21 G22. So let's write the formula for P in frame 0. That's going to be simply that rotation matrix we talked about, R10 times the position of P in frame 1. If you want, I can write it like this. Okay, so now let's sub in. R10 we wrote down as something to do with 270 plus theta 1. So I'm just going to write down the final formula which we get after I eliminate cosine 270 plus theta and so on. So I get, if you look back, it will be sine theta cosine theta minus cosine theta 1, everything is theta 1, sine theta 1. And then position of P in frame 1, which is now x1, which is this one, is going to be L0, right? Because length of link is L plus R10. So R10 is the same as what I written down here, sine theta 1 minus cosine theta 1, cosine theta 1, sine theta 1. Okay, so continuing this down, then we have R21, which is basically telling me how theta 2 is related to frame theta 1. That's simply cosine theta 2 minus sine theta 2 sine theta 2 cosine theta 2. That's the rotation formula. And then finally, position of G2 in frame 2, which is position of G2 in frame 2 from this origin. That's going to be simply C2 along X2 and 0 along Y2. So C2 and 0. Okay, so there's a little bit of math involved here. I frankly did not do this math by hand. I actually used MATLAB to do it. So I'm just going to write down the final answer and I'll show you later on how to do this in MATLAB. You probably also know how to do it in MATLAB if you practice doing symbolic notation. So it's going to be L sine theta 1, C2 sine theta 1 plus theta 2, and then minus L cosine theta 1 minus C2 cosine theta 1 plus theta 2. Okay, so if you want, let me just write it as xg0 y xg20 yg20, because that's going to be our notation for the position of point G in frame 0. Okay, so that's part 1 of the method to derive the Euler Lagrange equations. I also need to find, well, I forgot to find the velocity. So I need to find the velocity of G1 and G2. So that's simply x dot G1 and y dot G1. So that is essentially taking xg and using diff in MATLAB, and I talked about diff earlier, so I'm not going to spend the time doing that computation. So that is simply, let's call this VG1 equals C1 omega 1 cosine theta 1 C1 omega 1 sine theta 1, where I wrote down omega 1 to be theta 1 dot. So you'll see that it'll become function of theta 1 dot. And then VG2 is xg2 yg2 equals omega 1 c2 cosine theta 1 plus theta 2 plus L cosine theta 1 plus omega 2 c2 cosine theta 1 plus theta 2. And for velocity for G2 will be C2 sine theta 1 plus theta 2 plus L sine theta 1 plus omega 2 C2 sine theta 1 plus theta 2. Okay, so this is by far pretty intimidating to do by hand, and there's a chances you'll make an error. And what I recommend in this case is to just use MATLAB to do this differentiation. Yeah, that's how I figured out these values. Okay, and then I forgot to put down here, but omega 2 is theta 2 dot. Okay, so that completes step 1 for the deriving equations using Euler-Lagrange method. The second step is figure out the kinetic energy. That's half m1. It's going to be x dot g1 square plus y dot g1 square. So that's the kinetic energy of link 1, but that's only the translational part. There's also a rotational part because now we have inertia. So I'm going to denote I1 to be the inertia about the center of mass. Then the rotational energy is I1 omega 1 square plus, I have a similar term for second link, which is xg2 square. By the way, this should be in frame. All this is in frame 0. So the kinetic energy for the rotational kinetic energy for link 2 now is going to be not just omega 2 square, but it's going to be omega 1 plus omega 2 square. And that's because if you look at the link 2, this is theta 2, but the angle made by link 2 with the vertical is theta 1 plus theta 2. It's a link 1. And this is link 2. So because the angle made by the vertical is theta 1 plus theta 2, we have omega of link 2 is theta 1 dot plus theta 2 dot, which is omega 1 plus omega 2. And that's what figures out here. Okay, so that's the total kinetic energy. The potential energy is going to be mass of link 1, g, position of g1 in frame 0, plus m2g, position of g2 in frame 0. Okay, so the Lagrangian is t minus v. Okay, so now you can see how complex this is going to get. xg1 is, well, that's a simple formula for x dot g1 and y dot g1. But look at x dot g2. That's like a big expression. So if you try to take the square of that and then sum it, it's going to just be lots of lines of code. And then you've got to differentiate that. That's going to take an awful lot of time. And there's a possibility that you'll make an error. So really, I don't recommend doing these computations by hand. We'll use MATLAB to do them. Okay, so the last step after finding the Lagrangian is, okay, question, why not have potential energy also in state space representation? Can you rephrase? This is in state space? I mean matrix. Okay. First of all, the potential energy is a scalar. So if you want to write it as a matrix, you can write it as G transpose times the position vector. But I just think that people will be confused here. So let's just skip that. But yeah, you can write it as a matrix. So vector times a vector gives a scalar. That's what he meant. Okay, what is the last symbol in this? So this is how they usually represent Lagrangian. It's, if you like to call it L, that's fine. That's the Lagrangian. This is how they usually denote the Lagrangian. It's a special type of L, just a notation. I just write it as L in MATLAB. Okay, so finally, the Euler-Lagrange equations. Which are d dt dl dq dot j minus dl dq equals qj, where q equals theta 1 and theta 2. Okay, so when we do this math, which I suggest you do on computer because of the complexity of the expressions, you end up getting an equation which looks something like this. There will be a11 theta 1 double dot plus a12 theta 2 double dot equals a right hand side, and then a12 theta, sorry, a21 theta 1 double dot plus a22 theta 2 theta 2 double dot equals b2. So this is after simplifying this expression. Okay, and so what you need to do is we'll write this as a theta double dot equals b, where a is a11, a12, a21, a22, and b is b1, b2. Okay, and these a's are functions of, like theta, so it's theta 1, theta 2, and these a's and b are functions of theta 1, theta 2, omega 1, omega 2, m1, m2, I1, I2, C1, C2, L, and gravity. Again, it's pretty complex. You don't really have to know the form. All you need to do is simplify it in this form. Once you do that, you can find theta double dot, which is required for my integration, and that's found as a backslash p, and that's, remember, that's the inverse. The best way to find inverse in MATLAB is to do a backslash, numerically better than doing inverse a times p. This is same as inverse a times p. Okay, so once we get theta double dot, that was this is basically the equations of motion. Equations of motion. So remember, when we did the projectile, we were trying to get x double dot, y double dot. In this case, it's theta double dot what we are after. So once we get that, we can then integrate the equations of motion and then get the theta 1 and theta 2 and theta 1 dot and theta 2 dot, which is position and velocities of the links. And once we do that, we can do an animation. Okay, so next I'm going to show you how to do this in MATLAB. Okay, so, and does an animation. Okay, so first of all, I need to define all my symbolic variables. In this case, will be theta 1, theta 2, omega 1, omega 2. These alpha 1, alpha 2 are the accelerations, or d or angular acceleration, which is the rate of change of omega 1 and omega 2. And then mass, center of mass, and of course gravity. So xg1, yg1 is copy pasted from my notes to done as it is. Okay. Now for the velocity, I used a different formula. It's called a Jacobian. Okay. And so I'll write it down. I used Jacobian instead of diff, but bear with me. I'll show you what a Jacobian does in the next lecture, hopefully, or even this lecture if you're able to finish this. Jacobian is a even better way of finding the derivative of the velocity, or finding the derivative of the position to get the velocity. Okay, so I'll talk about the Jacobian in the next class. But you can do this same thing using differentiation and get the same answer as I have over here. I'll show it in the next class. I'll show you how diff and Jacobian gives the same answer for the velocity. Okay, so bear with me on this. So once I get the velocity, then I set up the kinetic energy, which is copy pasted from the formula. Here I used a different notation. Okay, instead of writing xg dot square plus yg dot square, I actually wrote vg1 times vg transpose times vg, and that's actually a more efficient way of trying to get the scalar. So what this is really is vg1 is xg1, x dot g1, and y g1. So when you do vg1 transpose times vg1, you can check this. It actually comes out to be square plus that square. You should check this. Okay, the rest of the part is the same as what I wrote down in my notes. Then the potential energy is same as in notes, and then I have the Lagrangian. Okay, now to use the Euler-Lagrange method, I had written down that formula, if you remember, which basically makes this very compact. The equations for Euler-Lagrange, they are basically over here. And then finally, I find the A matrix and B matrix. Again, I've used Jacobian, so bear with me. I'll show you what Jacobian does in a later class. But that's again an efficient way of finding out the A matrix, which I wrote down in my notes. So let's just run this. So here I'm going to show you print out A's, B's, and then pack them as an A matrix and B matrix. So let's run this. Okay, so that was pretty fast. So here's the kinetic energy if you wanted to see. Just keeps running. Okay, so that's why you don't want to use hand calculations. If you look at A11, that is also very long. I mean, A11 is not that long, but if you look at B1, B2, those are really long. Okay, so what I need to do is I usually take this part, which is the part I need to do the integration. I copy them into the file which does the integration. So this piece goes right in the place where I have my right hand side. So this is the same place as where I wrote the equations of motion of projectile. There was the gravity part, exactly that same place. I put these equations down, I copy paste them, and then I get alpha. And then alpha is basically, the first part gives me the rate of change of omega 1 and the rate of change of omega 2. And since this has two states, I need to define the velocity acceleration of link 1, velocity acceleration of link 2. Acceleration for link 1 and link 2. Okay, so let me just run this file. Okay, So that's a double pendulum for you. Let me run it again. I think it shows up on my other screen. Here it is. Okay, it also makes some plots. These are plots of position. Okay, in this case, position, I mean angular position, θ1, θ2, and then velocity. Okay, it looks pretty crazy. So the first part of the code is essentially setting up the parameters, doing ODE45, which is my chosen integrator here, and then doing plots and doing the animation. Okay. In this case, I also actually plotted the kinetic and potential energy. So the plot actually comes up as figure 2. So if you look at the total energy, what you expect is that total energy should be constant, right? Because this is a conservative system. So you can see that the energy is, well, it looks spiky, but it's actually not, because if you look at this axis here, the energy is 12 times 10 raised to negative 9. So this fluctuation is 1e negative 9, which is within the tolerance as specified here. So my tolerance for the integration was 1e negative 10, which means that I'm okay with 1e negative 9 fluctuation for my kinetic energy. So if I increase this to 12, then you see about 1e negative 11. Okay, so that's